Tom again. We're going to continue talking about Chapter 12 of RMT, and we talked about the shooting algorithm. And just to remind you what our strategy was going to be. First, we have this system of difference equations. We have a difference equation we want to solve. We boil it down to a difference equation in capital. Where did we get it from? We got it from combining the marginal conditions for the firm for capital accumulation, and the marginal condition, first order condition for consumers for intertemporal consumption. We boil it down to this one equation right here. We chose to write it, implicitly like this. First thing we did is we compute a steady state. We could do that almost analytically, and then we applied the shooting. We described how to apply the shooting algorithm to it. And this part, once we do that, we'll get a sequence of capital and consumption. We'll get an allocation, an equilibrium allocation in our competitive equilibrium with distorting taxes. And then once we do that, we'll get other objects. Once we've solved the capital sequence and the consumption sequence, we can get the prices from these equations, and then we can define some. What we do here is we define some rate of return concepts, and whether they're before tax or after tax. Kind of lets you look at that. So there's this definition of a. I urge you to study this. These are formulas for adjusted gross rates of return, in terms of which we can express. This is going to be kind of key. This is key. This is in a key equation to not only this model, but new Keynesian models. They all have an equation like this, where this is a consumption Euler equation. This R bar is the appropriate rate of return to put into that consumption Euler equation. So this would have implications for asset pricing models, in addition to what we're talking about. Okay, so we're going to. It's useful to stare at this, and what we do in this chapter is we do a little staring, and it's convenient to we'll take a parametric version of a utility function, a power utility function, and if you do that, you can get this nice expression that tightly links the rate of consumption growth and this gross rate of return on holdings of physical capital, gross rate of return to the household, and so this is another version of our equation that tightly links consumption growth to rates of return, and we're going to use that. So look at this sentence. Variations in distorting taxes have effects on consumption and investment that are intermediated through this equation. So so this equation always has to hold, and both C and R sequences adjust to make that hold. So now here's this. I told you if lump sum taxes aren't available, we have to do something like Braun or McGrattan did, to add an additional loop. It's basically adding an additional computational loop to our shooting algorithm, beyond the shooting algorithm. So this section you could skip for now, but you might know that it exists. This is a method that two really smart guys invented. Chris Sims, I think, was the first one to invent it, and then Prescott used it once. And it's another way to solve things, but kind of standing back and thinking differently about what's endogenous and exogenous. I'll just say that here. We're not going to use it to rest. Okay, so what we can do right away is we can get we can directly from the structures we can get some classic doctrines that are embedded in here. And I'll just go through list. I'll just tell you about, give you a little reader's guide. Lump sum taxes and Ricardian equivalents. You'll see this. So the timing of lump sum taxes has no effects on either prices or allocations. When the labor supply is inelastic, a constant tau n and tau c and tau n are not distorting. So tau n is not a distorting tax ever, because we have an inelastic labor supply. But tau in this context, but tau c will be non-distorting if it's constant. Variations over time in tau c, they are distorting on our definition, and capital taxes are always distorting. And you know, at root bottom, this is at the root. This is why many economists of all sort of ideological orientations think capital taxation is not a good idea. That there's better ways to tax. But at this point, we're not talking about better. We're just doing if then. So we're going to see some flavor. So we're going to do some transition experiments using the shooting algorithm. And now we're just going to kind of watch what happens. And then what I urge you to do is kind of think about your economic intuition. So as we do this. So we set some parameter values, and I'm going to set gamma. I'm going to have a constant relative risk aversion utility function, a power utility function, c to the 1 minus gamma over 1 minus gamma. We'll set gamma equal to 2. Lots of people think that that's realistic. And then what we're going to do is we're going to do an experiment that goes like this. Government expenditures, there's going to be a pre-announced. We're sitting here in a steady state, and here's government expenditures. Government expenditures are going to go like this, and then they're going to jump up forever, permanently. And they're going to do that at date t, and we're going to set t equal to 10. So there's going to be a foreseen increase in government expenditures, and we're going to keep everything else constant. So what that means is this increase, you know, at the margin, this increase is going to be financed by an increase in lump sum taxes. When? It doesn't matter. So what's going to happen is our equilibrium is a perfect four-side equilibrium that's been built in, and we're really stressing the point of view that dynamics is a special case of statics. We're doing this Arrow-Debreu style. So what's going to happen is before the date t, the variables are going to respond. So then read this paragraph carefully, because it kind of takes you into the structure of what's going on in these models. It's the essence of Robert Hall's famous paper that I mentioned at the beginning. So before date t, there's responses of endogenous variables that are due entirely to anticipation effects. Nothing's happened yet to anything exogenous, but it's going to happen, and those expectations have effects on on prices and quantities that precede them. Then they have effects after date t equals 10, because after date 10 they have effects because you've been knocked off a steady state, and it's going to take a while to converge back to a steady state. So there's anticipations of effects that happen before, and there's transient responses back to a steady state that happen after. So this before and after is gonna involve some mathematics that you've seen, and then this gamma parameter is going to be really important in what happens. So let's do the shooting algorithm, and let's turn it on in Python in some computer language. So here's what we got. So what we've plotted here, so it's a lot of fun to stare at this and figure out what's going on. It's actually fun to teach this to undergraduates. I'm going to teach one thing in macro, teaching the growth model with, first the growth model and then the growth model with distorting taxes. There's just a lot of macro and micro in it. Okay, so here's the dotted lines are the steady state, and we know how we computed that. We could pre-compute this. The dotted line was the initial steady state, and then what happens here is that's our graph. Government expenditures takes a jump, and then kind of what do we know? We know that government expenditures aren't in they're not in the formula for steady state capital. So what's going to happen is capital is eventually going to, we know in the limit capital is not going to change. But look, it changes in the meantime. Why? Notice that eta changes, the rental rate on capital changes, R bar changes, and consumption change, and they change in particular ways. So notice that there's a cusp in R bar. So there's a discontinuity in R bar, and there's a discontinuity in eta that occurs exactly at the jump point, but there's no discontinuity in C. And then you could ask yourself, why didn't C? See, this would have been feasible. It would have been feasible to have. It would have been feasible. So look at. I'll show you what solves feasibility. It's not going to be an equilibrium, but you could ask you why. G goes up. That's G. This would have been feasible. That's time. This would have been feasible. C, keep capital, don't do anything to capital. Keep consumption constant like this. And then have consumption jump down. And have capital just stay at the steady state. That's all feasible. Convince yourself of that. That's all feasible, but that does not happen. And you should ask yourself, why doesn't it happen? It doesn't happen in competitive equilibrium. And well, what does happen is this consumption, our consumers, they have utility functions that look like, it's got curvature. It's got curvature, and our consumer. Now this is tricky because this is a competitive equilibrium. Remember, there's no planner, or is there some kind of hidden planner here? And I'm not even going to take this up because there's this distorting thing, but there's still an invisible hand, because it's all decentralized, that's making things happen. So what our consumer does, it hates this. It hates this non-consumption smoothing, and it would like to make its consumption smoother. It would like to, maybe it would like to do this, but it can't do that because that's not feasible. So what is feasible, though, is what you notice what happens is what the consumer does is it immediately reduces consumption. It actually smooths it out like this. It reduces it. What it does is this. You see that? Because look here, it's having kind of the scales here are different. So look at the scales here. But what happens is the consumption immediately drops below its former steady state level, and then it continues smoothly to drop. There's an inflection point. It decreases at an increasing rate. There's an inflection point exactly where this jumps, where there's that kink, and then it smoothly glides in. So that's what happens, and all of this stuff, and what's happening is, well, how is that achieved? How is that smoothing done? Is, well, notice what people end up doing is they end up saving more. They end up accumulating, and they drive capital up in order to smooth things up, to smooth things out in equilibrium. So there's this smoothing that's going on, and the smoothing is occurring through capital accumulation. And what makes them want to do this? Well, prices adjust. I could have put the QT here, but the QT is implicitly here. These rates of return adjust to reconcile the firm and the household to society accumulating capital to smooth out this consumption. So the smoothing motive is dominant here. It's dominating. So now I could ask you, well, you'd think that gamma is a really influential parameter in determining the shape of this response. And if I increase gamma or decrease gamma, somehow the motives, that's going to alter this, how seriously people want a consumption smooth, and that's going to alter this, it's going to alter everything. So let's see what happens. We turn on the computer. Well, look what we did here. So spend some time with this. This is beautiful. What we did is we compared gamma equals 2 to gamma equals 0.2. So this guy, this has a lot of curvature. This has a lot of curvature. And this has less curvature. Much less curvature. So this guy with gamma equal 0.2 cares less about consumption smoothing. So look what happens. He cares less, so he does less of it. That's gamma equals 0.2. And this looks a lot more like the picture that I drew that said it was feasible to do it, but he chose not to do it. The society chose not to do it. And now you'll see capital accumulates much less, and the interest rate, there's less of an effective interest rate. These things are all tied together. And what's beautiful about this is we both have the foresight and the transient. These are foresight about things that will happen in the future, and transient responses to being off the steady state. Okay, so you could read those. Oh look, here I actually did compute the QTs. I computed the QTs, and for our two situations, I went back. So here was our C, and we could read off the altered. You see, it's the altered Q. The Q process changes in a way that reconciles the consumer to the new path that's chosen. Okay, so that's what's done here. And then what we do is we do other experiments. We'll do a response to a foreseen once and for all increase in tau c. A once and for all increase in the value added tax that's foreseen. There's a lot of payoff to studying what happens here. So lots of economic interpretations that can be gotten, all for the taste for consumption smoothing, and we can easily get the effects that occur on the interest rate and the term structure of interest rates. So that's what's done here over and over again. We do a foreseen jump in tau c. We do a foreseen jump in the tax on capital. We do lots of things. Okay. It's all I don't know, a way to read this is you get some feel for by staring at these and doing a few experiments and turning on the shooting algorithm. We get a feel for the consequences of various variations in various fiscal instruments, taxes on capital, labor, consumption. So, many of us have studied linear approximations to models like this, and this can be quite enlightening for doing this, because little knowledge of difference equations will take us a lot into give us some insights about what's going on in the experiments that we just did. So what's often done is to get a linear approximation. So let me just remind you how that's done, and then and what benefits it has, because then we're going to get an insight. So that's what this section's about. So here's a cookbook formula for how you get a linear approximation. So step 1, fix things at a steady state. Step 2, and then solve for k bar. Well, we already know how to do that. Get a first order Taylor series approximation around k bar or z bar, and if you do that, what you'll derive is a second order difference equation. So this is going to be a second order, it's a linear approximation around that. We get this second order difference equation, and now we just stare at it. Remember, z is this vector. We stare at it and rewrite it, and if we rewrite it, it's a k is a scalar, z is a vector. If we rewrite it, we get a second order difference equation that looks just like an example of something that's in chapter 2 of RMT, especially the appendix. Okay, so take that difference equation, and we use those lag operator methods that are in that appendix. We get the characteristic polynomial for this autonomous difference equation, call it phi of L kt plus 2. We use our tricks. We factor the polynomial, and when we factor the polynomial, we could do some rewriting, and what we can do is we just apply those appendix, I think it's appendix B of chapter 2, and we can get a solution a linear approximation to the solution. And what we find is that is this equation. This is the key equation. And you know, we could write this equation. If you're not comfortable with lag operators, we'll just rewrite it this way. This says that capital this period is equal to lambda 2, and lambda 2 is going to be a number that's between 0 and 1. Why? Well, you can read a little bit about that. And lambda 1 is going to be another number that's between 0 and 1. That came from this factorization. So it turns out that the law of motion, the equilibrium k sequence obeys this equation. K at time t plus 1 feeds back on k at t, and it feeds forward on all future z's with this geometric stuff. So this is a geometric sum of future z's. So this part is the foresight part. This is explaining why capital and consumption and other things are responding to anticipated changes in government expenditures or taxes. And this term is explaining, well, if you get bumped off a steady state, it's going to take a while to converge back. So this is the transient return to a steady state. That's called the feedback part. And this structure that's is present in lots of it's lots of rational expectations models. And then we know lots of things about the lambda i's, and they're connected to conditions for existence and uniqueness of an equilibrium with distorting taxes. And see, you can write down models, economies with distorting taxes, and competitive equilibrium with distorting taxes just won't exist. Or sometimes it'll exist and not be unique. And whether or not it exists and unique is closely linked to the values of the roots in a factorization like we obtained here. That's how that fits together. Okay. And then I'll show you a couple other things. There's lots of tricks with formulas. You could actually use you could actually either do it by hand, or you could actually get a formula for lambda 2, which is that return to the transient. That's analytic. You could do this by getting the computer to compute a bunch of things for you. And there's some insights about that conform to some of the intuition that we were talking about with those shapes of those graphs. Okay, so I think that's what I'm going to. I'll conclude now with just pointing to one other thing. An elastic labor supply. Okay. So if you Edward Prescott wrote an Ely lecture to the about 17 or 20 years ago at the American Economic Association, in which he was trying to explain why Europe has been less prosperous than the United States. And he uses a simple version of this model. And he uses it in a very special way. He just uses the model that we talked about now, but he now adds a preference for leisure, and we can do all this, and we can replicate our steps to steady state calculations, and we'll do some experiments. And if we do this, we will retrace some steps that we can, if we want, retrace some steps that Prescott took in his Ely lecture, and we will uncover something. There's a very important footnote in Prescott that he gets huge effects of taxes on labor on the equilibrium allocation. And he blames high taxes on labor for Europe's poor performance in his view. And what I advise you to look at is you can find here this little section, how Prescott makes that happen, even though many people expected it not to happen within a model like this. Because people had in mind some if-then statements, what Prescott really did is he changed the ifs. And he told you completely how he was doing it in a footnote, which would be easy to miss if you're not a careful reader. So this model that we have is a machine for doing many things. And then the last part of the chapter is a two-country version of the model that it's a version of a model that Mendoza and Tesser did, which I like a lot. I've kind of we've adapted it, and you can do lots of really nice two-country experiments with this using the shooting algorithm. So that's done in this chapter 2. I think there's kind of no substitutes for reading this and getting your hands on the difference equations and conceptually turning on the shooting algorithm. We have Spencer Lyon and Pablo Wanat made a really nice Python notebook with shooting algorithm which does some of these things, and I'd be happy to make that available to you. Okay, thank you.